Okay, so today for the IQIM seminar, we have Dominik Leichtle, and he's going to tell us about verification with minimal overhead and public verification of quantum computation.
Thanks a lot, Chris. Yeah, maybe I should say, so I'm a PhD student from Sorbonne University, Paris in France, as you can see from the slide. And I'm giving this talk on the occasion that I'll be actually visiting Caltech next week. So I'll be there from Monday to Friday. And I hope that I can interest enough of you with this talk that maybe some people want to talk to me while I'm there. Okay, so let's dive right in because I only got half an hour. So this whole thing is going to be driven by the motivation of quantum cloud computing. And so a lot of these companies that you can see here, and the list is by no means complete, are already getting into this. So we would expect that the first access that people are generally going to have to quantum computers is going to be maybe through the cloud. So just quantum computers are just going to be at a few centralized positions because not everyone can have a big device at home. They're going to be pricey. So they might need to delegate their computations to some more powerful quantum hub that's performing them for them. And so generally how this would look like then is we've got a client who's got no quantum capabilities or maybe very limited. So certainly not a full quantum computer. And they want to delegate the evaluation, for example, of some program to a much more powerful quantum server. So they would give them a function and some data and would like to receive the output then, a response from the server. And I think it's quite natural that the client in these settings will not just give away all of their data, that they would actually require some kind of security guarantees. So one thing that the client might want is that their data that they give to the server, but maybe even the program that they evaluate is kept from the server, is kept confidential. And this is something that in the setting we would call blindness, which means the client wants to delegate the computation to the server without leaking any information actually about the input data nor the computation, not even the output. So the server is just kind of kept blind. And the other property so the second one that I'm going to be talking about mainly, and you see this word everywhere already on the slides, is verification. And this is just the guarantee. The client wants to have the guarantee that the output that it receives from the server is correct, that the client's actually paying for a service that is actually, so that the function is actually evaluated correctly. So we want a certain kind of functionality built into this protocol, into this delegation, such that if the outcome that the server reports back to the client is correct, as in this case, the client is going to accept. And if it's not correct, the outcome, and this might be because the server is maliciously trying to cheat the client, or just because there's maybe too much noise, maybe the server is just not good enough to actually evaluate the function. Then the client should notice and reject at this point. So the client wants just to have the guarantee that the outcomes are good. Maybe I should say at this point that I'm not sure how it's common usually in the seminars, but I mean, if you have any questions, then do please interrupt me such that we can keep this interactive. So if there's anything unclear, then just interrupt me right away.
Hey, Dominic, sorry, I have a silly question.
There are no silly questions.
It appears to me that if you have blindness, then can't you is in the computation you can have like some very simple function evaluations to check if the result is being computed correctly? Doesn't it imply doesn't blindness imply verification somehow?
Yeah, I mean, so actually
universal thing.
Right. So in a way, this is what we are going to be doing, right? So we're going to use blindness to, I mean, there are already a lot of protocols that are using blindness to get verification then on top, but where blindness is essential to it, exactly to hide these kind of, simple computations, to these simple tests. So this is actually what's going to be happening. Yes.
So does it hold in general that any blind computation protocol can generically be converted to one which can be verified, or it has to be specifically tailored somehow? Or?
Yeah, so you could see this in a certain way as the result of the first protocol that I'm going to be talking about, to say that actually, if you do have blindness, then you get verification on top.
I see.
Yes.
Okay.
So this is
Thank
where I'm going to be going. Yeah. Now you already know
Thank
what it's going to be about. But good question. Yes. Right. So now this is a natural transition to actually what I'm going to be talking about. So it's all set in this delegated scenario where the client wants to somehow have both privacy of their data as well as verification. And the first project that I'm going to be talking about is about making this more practical, because there do exist blind and verified protocols that achieve this, but a lot of them come with a lot of overhead. So they're not just very easy to implement, maybe on current or even near-term hardware. And the other project, the second one, is going to be about extending the functionality of these kind of protocols and go to something, so get to something stronger, which we then call public verification. I'm going to explain later exactly what that means, but let's start with the first one. And this is maybe in a way already an answer to your question. So one thing that we obviously want is correctness. So generally cryptographically, this just means that if we have the protocol and it's run on perfect and honest devices, then it's going to do the right thing. So it's just going to accept, the client is going to accept, the verification is going to accept, and the client is going to get the correct output. But this is not super useful yet, because if there is a little bit of noise on the server side, then the protocol might just always abort, because a little bit of noise is not exactly the perfect behavior. And in this case, we might have a protocol that does just almost abort. This is still correct. So there is no, from a cryptographic perspective, this is not a problem, because we do not ever accept a wrong outcome, but it's still not useful. So what we want is something a little bit more powerful, which is robust correctness, which means that if there is a little bit of noise present on the server's device, then still it's going to go through, and we're actually going to get an output, I mean the correct output, and verification is then also going to accept. So we extend this correctness a little bit to also slightly noisy devices. Another problem with, and that I mentioned already with previous verification protocols, is that they often come with a large overhead. So a lot of them require, for example, full tolerant encoding to get to a decent security level. Often they also just require a large number of qubits or big quantum memory. So this is not something that we can expect maybe to run very soon. This is something that we can maybe expect to do far in the future, but it's not very useful so far. So the goal of this protocol was kind of to see how much can we cut here, how practical can we actually get doing verification without compromising the security guarantees. So we want to keep the same security guarantees as before, the full security against any kind of malicious attacks, but still cut as much as possible from this overhead. And well, in a way, to take this, to say this already now, what we've been able to show is that we don't need any kind of essential overhead except for a quantum channel. I mean, if we have a quantum channel, then we don't need any kind of overhead. So now to go a little bit into the details of the protocol, I need to give a tiny bit of background on measurement-based quantum computing. And this is the setting that it's in. So this is a model for quantum computations, and it's universal, so it's equivalent to the circuit model, for example. And how it works is that now all the computations are performed on so-called graph states. That means we've got these gray nodes, which are going to be just initialized with plus states. Then in the next step, they will be entangled along the edges of a graph, which is why it's called a graph state then. And finally, the server is going to measure these qubits one by one in rotated basis. And one can show that depending on the choice of these angles, one can actually perform now arbitrary computations like this. Not on a small graph on 5 qubits like this, but just as an example, I've I drew only 5 qubits here. So why we consider this model is because it actually makes it very, very intuitive to add these layers of blindness and verification to it. And since anyway it's equivalent, we could also express this in principle in the circuit model. So one could just translate it. So how does one add blindness to it? And you can see that this almost looks the same. What changed is that now the initialization of the qubits does not happen anymore in plus states, but in rotated plus states, so plus theta states. I should also say that this is not something that we invented, so this exists already. It's called the, I think, the Universal Blind Quantum Computing Protocol. And the idea is that now, once these initialization, these qubits that we initialize it with are rotated, we will also need to adjust the measurement angles in which these qubits are going to be measured. And this is just going to induce a natural one-time pad on them. So this is just going to hide all of these angles. And since the computation is encoded in these angles, it will hide the computation and also its output. So like this, we get more or less directly, we get blindness of our data and of the protocol. So this is already the first step. Now, how do we get robustness? So here we will need to restrict the computation that we're performing a little bit. Namely, we're going to be talking only about BQP computations now. So that means we don't have any quantum output. We only have classical output. And there is like one specific output that we would like to get at the end. And if you're in this setting, then actually robustness becomes simpler now because we can use classical error correction. Or I mean, in its simplest case, this just means we can repeat the computation multiple times, as you can see here. And if we know that the probability that one of them gives the correct output, I mean, the probability that a computation gives the correct output is not too low. More specifically, it's greater than 1/2. Then we know that with a high probability, a majority of those will have the correct output. So we can actually just perform a majority vote over the answers, and we're going to get the correct outcome with good probability, with exponential probability, actually in this case. So this is a fairly simple way of amplifying the probability to exponential that we get the right outcome, even in the presence of a little bit of noise. So this is how robustness works. And what's missing is the verification. So how do we get verification? The first idea, and that is, I think, already relating to maybe this is more or less what the question earlier was about, is that now since it's blind, we can just perform some other kind of computation on this graph that we know the outcome of, or that we can simulate or at least predict in any case. Perform this and then just see whether it matches our expectations, the measurement outcomes. So one could perform some kind of tomography probably on this graph, but this would work, but it's not very efficient. And there are actually more efficient ways of performing tests on this. And the one that we've been using was introduced as trap-based testing or trapification, because the idea is that we insert traps now into this graph. And a trap just means it's going to be a trap. In this case, it's a red qubit here in the lower right corner. And it's a trap because we will isolate it from the rest of the graph and from the rest of the computation. So we put in 0 or 1 states, which are the green ones here, all around the red one. These so-called dummy qubits, they only have the purpose of breaking the entanglement here at this point in the graph. So they will break the entanglement, isolate the red qubit, and now we can, because it's isolated from the rest, it's not entangled anymore, we can just perform a deterministic measurement on it, a deterministic single qubit measurement. So like this, we're going to be able to detect some kind of deviations that are happening in this part of the graph locally. Now, we cannot expect to detect deviations or errors that are happening in the rest of the graph. So we will need to also put traps in other parts of the graph, like this, for example. One can also put actually multiple traps at the same time in the graph, as long as all of them are separated by these dummies. And if we now go ahead and actually cover the whole graph with traps in different tests, such that every qubit is a trap and at least one of these different tests that we're performing, then one can show that this actually does detect any kind of deviation that could hurt the output of our computation. And this is now, well, fairly efficient, because it just depends on the number of tests that we need to perform. And this is going to depend on how many traps will be get into the graph at once. And just to mention this, this is then roughly going to depend on colorability of the graph, so the chromatic number. But still, it's, I mean, fairly efficient for graphs that are planar, for example, or at least not super highly connected. So practical ones, let's say. So to put this together, one could first perform some kind of tests on our device. So the client could first test the device, and then if it's good enough, perform the computation. But this is not good enough to get verification, because the server could change its behavior in between. Obviously, it could perform the tests honestly, then change its behavior and become malicious. So what we need to do is we need to actually permute all of these runs, so that we perform computations and tests at the same time. And now, because all of them are going to be blind, the server is not going to be able to distinguish which is going to be a test, which is a computation. So if any deviations are happening on his side, it might equally hit a test. And especially it might also equally hit any kind of our different test types, and therefore might be detected. So this is very roughly how we get then verification. And having this replication of computations at the same time, we are going to be able to tolerate a few failures, because we know that we can actually error correct them. So like this, we're going to get a mechanism where the tests are used to, in a way, assess how much noise is present during the execution of our computation. And if this noise level is small enough, then we can be sure that it's error corrected, and sure means we have exponential confidence, and the client can just accept at the end. And if it's beyond this, then we cannot be sure anymore that it's error corrected, then the client will need to abort. So the result is a protocol that is perfectly blind, only leaking the graph. Well, this we can't prevent, leaking kind of the amount of resources that are needed on the server, because the server always knows how many resources we use. We get exponential verification. We get an exponential probability that the protocol works and accepts if the noise is small enough. And crucially, we have no overhead in the size of the device now on the server side, because all of these tests are run on exactly the same kind of graph that the computations are running on. So we don't need a bigger device to perform verification at the same time. We actually just need to run it more often. What we do not do is any kind of fault tolerance. So since our protocol, so the robustness in our protocol only holds for a certain probability that one of these tests fails, a certain probability that one of these runs fails. It's actually, we do have a global noise level that we can tolerate. So it's not local noise that we can tolerate, and therefore we do not get scalable fault tolerance, because we somehow already need that global noise is small enough. So scaling this up, if we have a constant local noise, is just going to blow up, and our protocol is also going to abort all the time. So this isn't hard verification, but it's again useless because we don't have robustness. But in any case, we do have now robustness against constant global noise, and this in a way just decouples the fault tolerance that we need, fault tolerant encodings that we need to scale up our computation, from the kind of fault tolerant encodings that other protocols require to boost verification, to boost the soundness, which we can just do with classical codes. So in a way, one can probably also see this as a link between like full-fledged verification, which we get because we have these strong security guarantees, and benchmarking, on the other hand, which is much more efficient, doesn't have the guarantees, but well, our protocol is probably having the efficiency of benchmarking and the guarantees of verification in a way, one could say.
Did you combine your computation with a quantum code to get the scalable fault tolerance?
Yeah, that's something that you could do. So you could encode your computation, and then, or yeah, just generally, I mean, this is something that could basically happen under the hood on the server side. So the server could just perform everything on logical qubits in a way, and then if just the noise that is present on the server's device is small enough, then also few tests are going to fail, and yes, it's gonna run through.
So in principle, this first bullet point isn't such a big issue then?
No, I mean, we see this more as a decoupling, right? I mean, you can still put it together. Okay, it's more that we don't need the fault tolerance in our verification mechanisms.
Okay, I see.
So maybe just a word about security proof at a very high level. But I mean, I already mentioned it before, but the idea is that the server can distinguish between computation runs and test runs. So we can use the noise that we can detect in the test runs to conclude how much was present during computation runs. So if we can see that, now the other way around, a certain fraction of the test runs failed, then we can from there estimate how many of them were likely affected by just multiplying it with the probability that the minimum probability that a test run in which a deviation is present is going to fail. So we're going to get an estimate on how many of these test runs were most likely affected by deviations, and from there we can conclude how many of the computation runs were most likely affected by deviations. And if this is less than 1/2, then we know that we're in a regime where we can error correct. So essentially, this means that we show that any attack is either error correct with high probability, or it gets the attack that we avoid. So this project was actually born from the need to have some protocol that we can run on very small devices, because we were talking to experimental groups, mainly from Delft and Innsbruck. And they're trying to implement it as part of their Quantum Internet Alliance project. So they're trying to, they were basically looking for a protocol that they can implement on really, really small devices, which are connected there. And so this is the proposal that we made, and we were talking to them. And one of the problems that they had is that in their setups, a lot of aborts happen. So basically, a lot of times one of these runs would not succeed because something happened and they knew that it failed in a way, right? So they would lose a photon, for example, and they knew something went wrong. But if we would still count this as a failed run and add it to the noise, to our noise assessment, then the noise would just be way too large and the protocol wouldn't run anymore. So we were looking at this, and we found actually that these kind of aborts that happen early on in the protocol during a round, basically where the client or the server knows that something experimentally just went wrong. These we can actually ignore. So we can just restart this round, ignore it, and it's not going to hurt security at all. And this is something that actually makes this protocol then implementable in a way. Well, okay. So this is not the end of the line. One also needs to look at parameters, and there are trade-offs hidden in here, because we can basically get better robustness for less security and the other way around. And then if we want to have both, then the protocol is going to be less efficient because we need more rounds. So I mean, to actually then push this to hardware, one needs to look at these parameters as well. And there are some optimization problems hidden in here that need to be solved, but I'm not going to go into details. I'd rather talk a little bit more about some extensions which are ongoing work. So the protocol before this is published, Empirics, and I'm going to be talking about some ongoing work basically follow-up of this, which is not published yet. And so what we've been looking at is these test runs that we're running, because in computation rounds, the client is only preparing plus the test states. So they're all living in a single plane. And for these test rounds, the client needs to prepare these dummy qubits. So they're not in the same plane anymore. And it's a little bit odd to see that now there is some kind of overhead for verification, because for this testing, we need to prepare states that the client does not need to prepare if he just wants to run the computation. So we were asking ourselves whether it's possible to do testing without these 0-1 states. Another reason why this is interesting is that there are protocols, multi-party computing protocols, that are using verification as a core module under the hood somewhere. And it's kind of cheap to prepare these use these plus theta states in that protocol. But once the client needs to prepare a dummy qubit, so these 0-1 states which are outside of the plane, then in this protocol, there is a lot of overhead. So it's just not as efficient anymore, and we would like to get rid of these states. And then also the multi-party computing protocols that are based on this will become more efficient. So the question is, can we do something like this? Can we basically get tests where the client initializes the qubits now with states in a single plane, only in the XY plane, and then still perform testing on this? And while we were looking at this, the sad first answer that we found is no, because there is actually some specific deviation, some very specific deviation that we can show that is impossible to detect with these kind of mechanisms. And well, if we cannot detect all kind of deviations, then we can't be sure that the outcome that we get in the end is actually correct, because it might have been corrupted by one of those. And then we were looking at this even a little bit harder, and it occurred to us that actually this might not be a problem if the computation that we're performing does not mind these very specific kind of deviations, because it's really a very specific kind of error that we can detect. We can detect everything else except for this error. So if somehow we can get rid of this error without too much overhead, then it's going to be fine. And yeah, it turns out that we could actually design universal computation that is just naturally resistant to this kind of deviation. And then because we can detect all other kind of errors, the final answer is yes, because now we do have a computation that can just tolerate this error, so we don't need to detect it. And all other kind of deviations that might lead to a wrong result, we will detect and we can abort. So there are a lot more questions. For example, probably the most interesting is, can we do something like this for sampling? Since this is only working for BQP now, which is related to the fact that we need one specific determined output to be able to perform this amplification mechanism that we're doing. And we don't know how to do this yet. So we can run the same protocol for sampling problems, and we will get polynomial verification, but we do not know how to get this to exponential yet. So this would be a really interesting question. Also, it would be interesting to see whether, for example, we can get rid of the quantum channel that we have in the protocol, make a classical client protocol out of this, maybe at the expense of then adding overhead again on the server side. Applying this to other cryptographic protocols, as I mentioned, or since this protocol is now so efficient, it kind of seems to just work well in a quantum internet environment where there is single qubit quantum communication. And then maybe we can just actually integrate this like more at the bottom of the stack somewhere. Okay, so I think maybe I have a few more minutes. Okay. Then I'll use these few minutes that I still have to say a few words on the second project that I would like to present on public verification. Unless there are actually any questions right now about the first one so far.
I have a question.
Yes.
What do you see? You have these trapped qubits, and I guess their location is not supposed to be known to the server.
Yes, that's correct.
How do you guarantee that again? I think I missed that point.
Yeah, so we're doing this by adding this blindness technique on top of it. So all of these computations that we're performing, both computations and tests, they are going to be blinded in a way that they look all the same to the server. So the server is not going to be able to distinguish different kind of tests. So which means tests where the traps are in different positions, and the server is not even going to be able to distinguish between tests and computations.
And the blindness, so somehow that resulted from just picking different angles for the initial qubit initialization?
Yes. So basically, this is coming from the fact that we can one-time pad the input, the description of the program that we're running, and the outcome, and the price for it is that we have now a single qubit communication, because the client basically encodes this one-time pad in quantum states and sends them to the server. So this is kind of the price for it.
Oh, you're saying the program is encoded in the data? Is that what you told me? Or in the wave function?
So the program is encoded in these measurement angles. So if I just go here to this, back to this graph, for example, the evaluation of the program works by just measuring these qubits one by one on the server side in rotated basis. And this rotation, the rotation angle, if you take all of these together, then this is an encoding of the protocol, an encoding of the program, sorry.
I see. I guess I have to figure that out. Maybe I'll ask you after. Thanks.
Yeah, maybe I can explain a little bit more at the end.
Experimentally, is it easy to like so I guess like these provided qubits might be like, say, like photons or something like this. Is it easy to prepare these arbitrary angle states?
Yeah, so as far as I need to say that you probably should take this with a grain of salt, because I'm not an experimentalist. But the people that I've been talking to, they seem much more concerned actually with the entanglement. So the preparation of these states. Okay, basically, the groups that we've been talking to within the Quantum Internet Alliance, how they realize this quantum communication is by actually distributing bell pairs. Where one side went to the client and one to the server, and then the client just measured their qubit in a rotated basis and generated then a rotated plus state on the server side like this. And I think these rotated measurements, these rotations, they weren't so much the issue. The entanglement was much more the problem, I think, actually, in this case.
Okay.
So actually, what might be interesting actually as well is that, so all of what we've been doing here, it doesn't work only in the setting where the client prepares single qubits and sends them to the server, but there is another model which is, well, almost equivalent, one can say, where the server generates these kind of graph states to begin with, these kind of resources, and sends them one by one to the client, who then measures them. So the different setting here is that the client does not need to prepare single qubit states and send them, but rather receive single qubit states and perform measurements in them. So this is kind of their limited ability. And one can do the same thing in the other setting as well. So this is like it's the same protocol without major modifications that you can do. And I think people have been arguing that this might be a little bit more feasible maybe to realize, because one could use a source for these kind of bigger resources that we need on the server side, rather than actually entangling them, building them from the ground up from these single qubit sets.
So in that scenario, then the thing that the server provides is some resource state, and you want to make sure that it's not been tampered with. Then
yes, basically what the tests are doing is just testing this resource. Then yes.
And is the protocol that you present like in some sense also resistant with respect to state preparation errors on the side of the verifier?
Right. So this is a really good question, because this is actually also ongoing work. It is, as long as these. So let's put it like this: the proofs that we have, they directly apply to the case where there are errors present on the client's device, as long as they are independent of the secrets. Okay. So if basically there is noise present, but it's independent of the rotation of the angle, then yes, everything's fine, it goes through. Now, if it starts to depend on the secrets, then things don't work anymore the same way, because there might be now a leakage of these one-time.
Sure. Yeah. I guess in the first case, you can always blame the prover for these errors or something like this.
Exactly. And in the second case, we're actually currently looking at ways of maybe then using privacy amplifications mechanisms to get rid of this dependence and to get back to the case where it doesn't depend on the secret.
I see. Thanks.
And then we're good again. Yeah. But this is this is still very, very new, these ideas. Okay. Then maybe I proceed to the second project, which is not going to be as long. I just want to give an impression of it because I find it somehow very interesting. And so maybe I start with describing the conflict and the reason why we need new functionality. So let's assume that you have a verified blind quantum computing protocol, one of the type that I presented just now. And you're in one of these two scenarios. So in scenario one, the server is malicious or there is noise present, and therefore the verification fails. And the client's going to reject in the end. And scenario two is the server is actually honest, but the client is tampering with its own verification mechanisms to make it fail on purpose. Such that at the end, the client can claim, well, verification failed, I'm not going to pay you for the service. Because, well, obviously, your device is not good enough. And in scenario two, if the client maybe does that in a smart way, it might still get the right outcome. So it would be like free computations for the client. So this is something that we want to prevent. And the problem with current VBQC protocols is that they cannot distinguish between these two scenarios from third person's perspective. So if these two go now to a judge, there is no way the judge can tell whether the trouble came from the client side or from the server side. So this is the protocol that we try to resolve here. I'm just going to present a couple of ingredients that we use to realize this without going through the whole protocol because it's a little bit cumbersome maybe. And so the first ingredient is a broadcast channel. And this is something that we know from classical protocols that want to achieve a similar kind of functionality, public verification in classical. They require a broadcast channel. So a broadcast channel just means that you've got some kind of a bus, and all the information that is written to it is going to be available to everyone in the world. Everyone's going to see it. So especially also the judge, which means the judge is going to be passive in the protocol, in the sense that he's not going to be sending any information to other parties. He's not going to send any messages, but he will need to be able to receive messages over this broadcast channel. But basically, he's just going to get a transcript of the communication in the end. So the trouble now with quantum is that it's not clear what quantum broadcast channel is supposed to mean, because I mean, if we have quantum states and we can't clone them, then how are we going to distribute them around? And this question is actually related to the question of, can we prove the transmission of a quantum state? So there is a lot of trouble kind of that arises now once we are in the quantum setting. And we are, well, solving or circumventing this problem by actually just pushing all quantum communication that we have into a initialization phase. So we will have two phases in the protocol. And the first phase is going to consist of quantum communication as well. And the online phase then of the protocol is going to consist only of classical communication over the broadcast channel. And it's only the second part that we're going to be able to publicly verify. On the other hand, since the first stage is only some kind of a initialization phase, resource preparation, it is not going to depend on the input of the client. It's not going to depend on the computation that we want to perform. So this is really just distributing resources in a way over the quantum channel. Now, the second ingredient is trap verification. That means we are using a protocol similar to the one that I've been talking about earlier under the hood. So there are going to be these kind of trap mechanisms that will detect deviations. Now we need to make sure that the client did not set them up in a wrong way to make them fail on purpose. So what we will need to do and this is now what's happening in the initialization phase, is some kind of trap verification where the server verifies now the other way around that the client has been setting up these resources correctly. We do this by running some kind of cut and choose scheme. And so the nice part is that while cut and choose only gives us polynomial security generally, and I don't think anyone knows yet how to get beyond this, we can take care of this and the rest of the protocol and perform an amplification in the online stage that then makes exponential security out of this actually. So there is going to be exponential security on the server side in the end that these resources have been set up in a correct way. And the third ingredient is something that we call double blindness. Now, in the original protocol, the server's been blind already. So that means the server doesn't get any kind of information about the computation, about its inputs. But we can imagine that in the case of an abort, the client will actually still get some information from the protocol, for example, intermediate results. And this is something that we want to prevent, to take even more incentive from the client to cheat here. So what we're doing is we're actually blinding the client as well during the protocol and delaying any kind of information flow to the client until the very end, after the verification stage, such that only once the client accepts the outcome of the computation, then the client will actually receive the outputs of the computation. And then like the tricky part is here, how to do how to run the verification mechanisms on the client side while keeping the client blind at the same time. But this is roughly what we're doing. And okay, obviously the judge is also blind. So there is no information leaked also to third parties. So in the end, it's a protocol where everyone's blind, no one knows what's going on. So putting these ingredients together, one can then construct this protocol which has blindness against the server, blindness against the judge, blindness against the client in case of aborts. We've got exponential verification for the client against malicious servers. We've got exponential verification for the server against malicious clients. And well, all of this for, let's say, only a polynomial overhead in quantum communication. So it is efficient in an asymptotic sense. Yeah, so this is nice because it actually gives the first publicly verifiable protocol now over a quantum channel, and then we can actually go further, replace the quantum channel by classical client remote state preparation functionality. So it's basically just classical client protocols that work over a classical channel and that require now some kind of classic cryptography, post-quantum cryptography. And like this, we can make this a classical client publicly verifiable protocol, which is the first of its kind. So for example, if you compare this to Mahada's protocol, then I mean, this protocol is verifiable, but it's not publicly verifiable. So it cannot yet resolve this conflict that I was talking about earlier. And yeah, this just brings me to some more open questions. The first being, can we do public verification maybe with less overhead than what we have? Because we still require now quite a bit more communication. Actually, what I didn't say is that also the device on the server is now quite a bit bigger than what we would require if we wouldn't run the public verification. So can we just do this with maybe less overhead? Maybe can we do public verification for specific algorithms only if we don't care about the blindness of them, and then make it even more efficient? And yeah, and then something that was just a very basic idea so far is like, maybe this is somehow useful for public quantum money, because also there, I think they require some kinds of public verification mechanisms, but I'm really not an expert on this. So maybe if someone of you knows more, maybe you can help whether this is actually interesting for quantum money or not. And yeah, so this brings me to the end. And sorry that this was a little bit more than half an hour. Yeah, so if you have questions, then ask now or ask me next week, because I'm going to be around at Caltech till Friday. So I'm going to be around the whole week and hope for many discussions. And yeah, maybe I can see some of you in person.
Thank you for the nice talk. So I have a question. So I guess overall, if we wanted to actually, or if we wanted to do one of these schemes kind of in the near term, what sort of like, I guess like what's like the minimum amount of features that we need, like capabilities that we need to do this, I guess.
Yes. So, well, I guess you're referring to the first protocol because the second one is kind of out of reach so far. Also the second protocol actually, so the publicly verifiable protocol is not robust. So also there, any kind of noise is just going to cause immediate aborts. Yeah, so for the first protocol, actually, I think people have now started implementing it. So there is hope that one can do it. But they're doing it on really small devices. So I think their server right now is 3 qubits only, which is because they're using photonics, and then they just can't scale it up because I think the issue that they have is that any kind of entanglement that they need to perform has another big failure probability. And then just, I mean, if you do a couple of these operations, and there is just no probability left that actually all of them succeed. Yeah, so coming from this perspective, it seems like it would be important to get these better. Also for the protocol, we need, obviously we need quantum communication. So at the same time, it kind of seems to be predetermined for photonics maybe. I mean, or at least let's say if you would want to do this for superconducting, yeah, I don't think we can get communication so far. So we have a big server, but we can't actually get the states there. Yeah,
I think there's a few experimental groups that are working on sort of, it goes by this name, optical to microwave transduction, to sort of various schemes to get a photon state into qubit, or into like your computational degree of freedom.
Yeah, so this would be super interesting, obviously, for us then. I mean, if you can get somehow a little bit bigger device on the server side and still get qubits into it, then yeah, this would be amazing.
Also, like how important is it that actually there is a quantum channel in the physical sense that in the security proof, I guess, whenever the quantum state sweeper by the verifier leaves the home of the verifier, then all the I guess you assume that the prover can also tamper with the channel or whatever happens. So I guess in some demonstration, even if in the same quantum circuit you would have state preparation and then all the rest you consider as the prover, I guess it doesn't really matter. I mean, that there's some proper distance. And I mean, it does matter for proper applications, but I guess for a demonstration, you could think of just running the circuit and saying, this part is the verifier, this part is the prover. Absolutely.
Yes, absolutely. You could absolutely do this. In the end, I think it just boils down to a matter of like trust, which hardware do you trust and which don't you?
Sure.
So there were attempts also to reduce this even further and maybe just have a single, let's say a single rotation that we need to trust. So for example, can we do similar things if we have on the server side just one gate that we can control from the outside, and that we trust and we assume that it doesn't leak any kind of knowledge about its instructions to the rest. So kind of that its noise is independent of the noise maybe of the rest or something like this. And then there is hope that we can still do similar things.
Okay. Thanks.
So yes, you can do this. Also, what one can obviously do is just like cut the server in half and say, or like just cut off a small part and say, we trust this now, and this is going to be the state preparation, and then the rest can happen, whatever.
Yeah, but I see why in photonics it's maybe more natural because you can essentially put some distance quite more easily between different parts of your experiment. So yeah.
Yes. Yeah, I mean, you can implement this on other hardware as well. It's just that you might need to take a few more assumptions on parts of this device.
Okay.
I also have a small silly question. So for the first part of the talk, first of all, it sounds really interesting. Like the second result sounds really interesting. to be able to do the whole thing. So it's really cool. Yeah. So for the first part, I was wondering, like you mentioned, there's this robust correctness and all of these nice properties, but you require quantum communication. I was wondering why we can't use. I'm guessing there's an obvious reason. Why we can't use like this post-quantum state preparation like you did in the second step.
Yes, so this is something that I, oops, where is this? Here, so this is what I meant when talking about combination with classical client protocols. The question, can we get rid of the quantum channel by replacing it? Some functionality that uses post-quantum crypto to remotely prepare the state while it's still keeping it blind, hidden from the server. And yeah, I would assume that this is something that we can do, but I mean, it comes as at a certain cost, because now to run this functionality, we will need to run, generally, I think these require to run, like to evaluate some kind of cryptographic function, this post-quantum function in superposition. So this requires us to like perform arithmetic on, like, I don't know, maybe thousands of qubits or something. Yeah, so one can do this, but then, I mean, it comes at a price.
Right. So you're saying that it kind of requires some sort of fault tolerance already on the side of the server, or it's too big, or
yeah, I mean, it requires just so yeah, it increases the size of the server by a lot in this case. I mean, if we're talking about small instances, maybe if we're talking maybe asymptotically it doesn't do much, but for small instances it adds a lot of qubits. And yes, so we can, I mean, for current devices, there might just be too much noise. So, I mean, even if we would do like a miniature version of, let's say, a remote state preparation, even though that probably doesn't come with any kind of security actually, but one could think about like running a toy model. But even there, I'm not sure if there is hope that we can actually evaluate this and get something that is not just super noisy, not just randomness.
Thank you.
And is there hope to obtain, like, I don't know, better post-quantum gadgets that allows us to do these constructions, or is there kind of a fundamental like lower bound on the number of qubits one should expect to have these kind of protocols? So maybe there is hope to optimize this a little bit further, but there is certainly a lower bound, because once so I mean, they usually put computational constraints on the server. So we're saying that the server cannot break this post-quantum crypto, but it also means to keep the state hidden from the server is not going to should not be able to actually simulate what's going on in this gadget. So this means it does need to have a certain size. I see. If it's like, let's say below 100 qubits or so, then we're getting dangerously close to a regime where the server is just going to be able probably to classically simulate what's going on there, and then we lose security. Okay, so yes, there is a natural lower bound in a way.
Great. So thanks for the nice talk, Dominik. I would clap, but that's kind of awkward over Zoom. So
yeah. Thanks a lot for the invitation.